Hey gang, Math 6610, going to go through a complete example of Anova from cleansing data to, um, let's get this straight here, that's going to kind of bug me. From cleansing data to checking um, assumptions to looking at descriptives, carrying out the Anova, conducting a post hoc with a new way that using Bonferroni, which may be a little bit more appropriate than Tukey, um, and even getting into effect size. So there's going to be a lot going on here. I don't know how long this video is going to take, but I have allowed it to be almost 2 hours. So hopefully we don't go that long. And if we do, I'll probably split it into two videos. But anyway, what I want to do here is, number one, we're going to access a data set, and this is just some quiz scores across professors. I made it up to achieve a goal, so nothing that's extremely creative. I want you to be able to obviously cleanse the data, and I'll show you what I mean by that. And I want you obviously to be able to import into R so we can analyze the data. Next thing we'll do is check assumptions. And the assumptions, although we don't have a test that we check for independence, we'll talk about that a little bit. Equal variances. I'll even tell you what happens when this is violated, and of course normality. And we'll get into some new stuff here called uh, normality and what we call multivariate normality. The third thing we'll do is we'll conduct the Anova and talk about what the results mean. And then we'll do a post hoc analysis, and I'm going to introduce the Bonferroni approach. And then we'll get into probably more than you ever cared to know about effect sizes. So, guys, what you can do is, again, 6610, 6620 is just trying to get you ready for the thesis, the master's thesis, uh, for if you complete the program. Keep in mind that if you get into your research, into your thesis, and you need to conduct an ANOVA, then all you need to do is just come back to this video, and I'm going to tell you everything you need to know to conduct an ANOVA at the research level. So I noticed my last group, what I call the 2012 cohort. I noticed when they did when they were doing their research and when they were doing their statistical analysis that if they ran into like an ANOVA, they'd get online and start searching up how to do an ANOVA. I'm like, dude, I taught you how to do that in 6610. Why are you wasting your time? So, guys, this video will stay on YouTube. I am not going to delete it. So, and also you're going to need some of this stuff for your assignment, which I think this is week. I don't know what week it is, but your first assignment is coming up very, very, very soon. So, guys, let's get going. The first thing I want you to do is go to Blackboard, and you're going to find a data set. And I think I called the data set quiz prof. I'm not really sure what it is, but I call it something like that. So I already have the data set. Let me get out of this. There we go. I have a quiz scores, so scratch that. I have it called quiz scores, and I have it on my desktop. All right, gang, so this is what we got. We got a harmless looking data set here where we have Professor A, Professor B, and Professor C. These are 7-point quizzes. So you can just eyeball this and see that it appears that Professor C's students, these 5 randomly selected students, perform better than Professor A and Professor B, but we don't know that yet until we carry out the test. So again, not an extremely interesting data set, but nevertheless something that we're going to use to examine ANOVA. So first thing I'd want to do is I'd want to put my quiz scores in one column. So I'm just going to do a copy and a paste. So I consider this to be the entry level cleansing your data. Now, when we get out in the real world and start collecting data, you're going to see that you're going to have missing data. And we'll talk about that later in the class. How do we handle missing data? Now, the next thing I want to do here is just set up the professor. And it looks like the first 5 were A. Hope that's 5. The next 5 were B. And the next were C. And this is something you could even do with high school students. This is a harmless data set, simple, something you could get into descriptive statistics and so on. All right, gang, so we've got our quiz scores over our professors, and we've got this ready to put into R and actually start conducting the ANOVA. First of all, I need to come in and do a save as. And I'm going to call this quiz scores. I'm just going to call it quiz. And desktop, and I want to comma separated values. So CSV. Now guys, again, I had a student in here this morning that came down here and was farting around with Windows comma separated value and MS-DOS. That's not what we want. We want this one right here. All right, so let's save it and save it to the desktop and hit continue. Let's close this down, get rid of it. I've already saved it, don't need any of that stuff. And let's just get rid of Excel so because I want to. All right, let's bring up R. And I don't want to bring that up. I want to bring up R. I don't know why in the world I clicked that. And just like before, let's set our working directory. I think it helps to get the working directory, see what things look like. Let's go get our data. I'm always really clever. I call mine data, and we call this quiz. Let's attach our data, and then I always like to look at the variable names of quiz and prof. And if this kind of stuff turns you on, just go ahead and do data, and you can see your data set. There it is. We have 15 subjects across 3 professors. All right. So the very first thing I'd want to do is I'd probably want to take a look at some descriptives. So first I'd examine descriptives. And what you got to think about descriptives are descriptive statistics just tell you important characteristics about these 15 kids or these 15 students. I guess professor, they would be at the college level. So these 15 students. Something I may want to do is I may want to look at a box plot of my quiz scores. And I can see I have a relatively symmetric distribution with no outliers. I may want to look at a histogram of my quiz scores. We have a positively skewed distribution of all the quiz scores. Now that may be an issue if we were getting into some sort of regression analysis. It looks like to me that the equal variance assumption, or I'm sorry, the normality assumption may be violated, but more about that in just a second. We really don't concern ourselves as much with the normality assumption for the variable quiz. We look at the multivariate normality as are each of these distributions, the distribution of quiz scores for A, distribution for B, and distribution for C, are they kind of internally normally distributed. So we're more interested in the histogram of quizzes across professor, distribution shapes, I should say. Now, one other thing I could do that may be kind of cool is I could look at my quiz scores across the professor. And just as we thought that Professor C's scores appear to be pretty high. And if we look at the lowest score for Professor C is equivalent to Q3 for Professor A. So I'm expecting the Anova to probably be statistically significant here. Okay. Now, other things I'd want to do is I'd want to, take a look at just basic descriptive statistics of quiz. So the mean and the standard deviation. And I'd probably want to look at the variance. And I see nothing at all wrong with looking at the 5-number summary. But guys, what I'd want to do here, I'd want to do type equal 2 so I can get the Q1 median and Q3 that correspond with the traditional way of calculating those things. But probably more appropriate would be to look at the means across professors. And as we've talked about before, we can do that with t-apply. So I can do quiz across prof, and I can look at the mean. And I can see that the average quiz score across professor is higher for C, Professor C, than it is Professor A. But again, I don't know yet whether this difference is statistically significant. And this is something that drives me insane. My dad and I got in a big debate. I still think it's funny that he debated me over statistics, but we got in a debate over the presidential polls because he's really obsessed with stuff like that. And I love how they'll say that candidate A is leading candidate B because the recent poll shows that they scored 48% versus 46%. Well, guys, you got to remember that 48% is specific to the, say, 1,000 people that were polled or asked who they currently support in the presidential election. You have to look at the margin of error. You have to look at the confidence interval to be able to generalize these statements to the entire population. Well, same thing right here. This mean of 5 is specific to these 5 students. And we could use that to estimate the mean score I'm sorry, this is Professor C. So it would be these 5 students. So these 5 students were randomly selected from a large group of students for Professor C. So that 5 is not the mean score for all students for Professor C. It's just the mean score for these 5 students. So keep that in mind. Okay, that's an important point in statistics. All right, guys. Mean. We could look at the standard deviation. We can look at the variance. We can look at whatever we need to look at. And we're going to get into that more here in just a second. All right, gang. Next thing I'd want to do is check assumptions. And the first assumption is probably the best to, or where we should actually start, is probably checking the equal variance assumption. And to check the equal variance assumption, we're going to have to load the package car. Now, if you have loaded car previously, then all you have to do is just access by the library by typing library car and let it go through its whatever it needs to go through. I remember a student last semester, we had the darndest time trying to figure out why she couldn't load the package car. Well, it turns out every time she tried to install the package, she was putting in cars with an S. So guys, if this is the first time you've installed car, then you'll need to go through the install packages. It'll give a window will pop up with to select the CRAN, go down to USA, California 2, to the UCLA folks, and install that one. But I've already done that, so I already have the package installed. I just need to access its library. Now, it's really cool. Once we do that, we can just do what's called Lavigne Test, and we want our dependent variable across the group, and we want to use center equal mean. Now, when I do that, you can see that we, right off the bat, we kind of get tunnel vision here and look at the p-value. And the p-value is only meaningful if we know the context of the calculation of the probability. Remember, the probability is based on the assumption that the null hypothesis is true. This is the probability of getting our sample of this level or more extreme. So it's in the context of the null hypothesis. Well, guys, the null hypothesis here is that the distribution is normally distributed. I should say the population, where the alternative is population is not normally distributed. What am I talking about? Oh, I've lost my mind, guys. I'm already thinking about Shapiro test. We're testing about equal variances. Oh my gosh, that was awful. So that is not the null. The null is the variance are equal. Gosh, that's horrible. I would tell you that's the first mistake I've ever made, but I don't think you guys would buy that. So guys, the null is the population variances are equal, and the alternative is population variances are not equal. That was so absurd it makes me laugh. So we have a p-value of 0.913, so we would fail to reject the null. So we can conclude that what we can conclude is that we can't reject the statement that the population variances are equal. It doesn't mean the population variances are equal, and I want to make that stress that. A lot of people want to run out and say that, say, well, we have equal variances because our p-value is greater than 0.05. It doesn't say that. There's just not enough information. There's not enough statistical evidence from our sample standard deviation, I'm sorry, sample variances to conclude that we should reject that statement. So we kind of leave the test thinking it's more believable that the population variances are equal than not being equal, than they are not equal. But we can't just give in to the statement that the population variances, are equal. All right, let's hope this gets better. Hopefully I'm not stating null hypotheses for a wrong test very long. Next thing I'd want to do is check normality. And the first thing I would want to do is just check normality for the quiz scores. Not necessarily look at these things over professor and get into the multivariate normality test, but just check normality for quiz scores as a whole. Now, gang, to be able to do that, we need what's called a Shapiro-Wilk. So the Shapiro-Wilk test is what we'll use to test normality. Now, I've been dying to do this. So the null is the population is normally distributed, and the alternative is the population is not normally distributed. Now, based on the histogram that we got for our sample, that histogram, and let me just go ahead and bring it up. Again, we never speak of a distribution of sample scores in terms of a normal distribution. Normal distributions are these theoretical distributions that represent populations. These group of students are a sample, they constitute a sample. But so we could get a bell-shaped and symmetric distribution, we could get a positively or negatively skewed distribution, but we're trying to generalize from this to the parent population distribution shape. It's kind of like if we want to know the average ACT score for all students at Shawnee State University, and we go out here and select 100 students randomly, and we get their ACT score, and let's say it's 22.8. There's no reason for us to believe that the average ACT score for all students at Shawnee State University is 22.8. All we can say is the 22.8 is the average of those 100 students. We have to use inference procedures to generalize to our population. Well, same thing is going here. We can look at this histogram we can look at this histogram for our sample and kind of eyeball it and think, is it reasonable to think that this distribution could happen from a population that's normally distributed? Could we pull out these 15 students at random and get a histogram that looks like that if we're pulling from a population distribution that's normally distributed? Well, it doesn't look like it to me, but we probably don't have enough power because of our small data set to reject the null, but let's just go ahead and run it anyway. So guys, it's really easy to run. Just run your Shapiro .test over the quiz score, and again, our null hypothesis is the population is normally distributed. So it follows the W distribution with a p-value of 0.58. So we would fail to reject the null. And again, that doesn't say that our population is normally distributed. It just says that based on this test result, there's not enough evidence to reject that statement. And that's all it says. Again, it does not say our population is normally distributed. It simply says there is not enough statistical evidence from this sample to reject the statement that this distribution, that this sample came from a population that's normally distributed. Now, what's far more interesting and worthwhile, and I guess I could say far more interesting and more informative, is what we call multivariate normality. And what I want to look at there is I want to conduct this test across each group. So look at it separately for Professor A scores, Professor B, and Professor C. And it turns out this is easily done. We can use the by function and use our quiz across our prof, and we can just do the Shapiro, Shapiro test. Now, this is really cool because, what it does, it breaks it down for Professor A, Professor B, and Professor C, which is nicely done. So you can see that for each of these, the p-values are greater than 0.05, so we cannot reject the claim that these distributions across, that this sample across each of the professors doesn't appear or appears to come from a distribution that's not normally distributed. So we don't get statistical significance, so we can go ahead and assume that we satisfy the assumption of multivariate normality. Now, what do you do if you do violate one of these? Well, that will take an entire video for me to talk about that. So let's go ahead, and I'll let's see, probably maybe later this week or maybe even next week, I'll put up a video on what happens if you violate normality. It actually turns out there's a guy that used to be out of the University of Cincinnati named Stevens that did a lot of work on this, and he actually found that violating the normality assumption isn't really that big of a deal. If you're publishing something and you violate the normality assumption, just report it, and you can really kind of go ahead and run your Anova in this case, and feel pretty confident that there's not much difference between the p-value that you calculate and the true p-value that you would get if you didn't violate the assumption. Well, guys, independence. What I would want to do here is I would want to make sure that the samples weren't related. I'd want to make sure that the experimental design. I want to make sure that these students weren't cherry picked. Maybe they decided to only select the students who sit on the first row, or whatever. So, but we're going to assume that the independence assumption was handled in the design of the study. Guys, now comes the fun part. Let's run the Anova. And I'm going to call it model. I'm just going to run the Anova of the quiz across professor. And we'll come in with our summary of the model. And the very first thing we'll look at is the p-value. So what we have here is we have statistical significance at the 0.05 level. And it'll help you here. It's got 1 asterisk. So if you come down to 1 asterisk, you can see it's statistically significant at the 0.05 level. Now, in a previous video, I talked about how we report p-values. So hopefully you watched that. You should have. There's no reason not to. If you didn't, you need to take a look at that. All right, gang, we really don't know a lot now. It's kind of like a chi-square test. That's something I'm going to talk about maybe in our next video, I think. What do you really know when you get, you've got a 2x2 contingency table, 2 categorical variables. You get a chi-squared, p-value of 0.01. You reject the null. What do you really know? You really don't know much. And at this point, we really don't know much. We know that at least one pair of means appears to be statistically significant. So guys, when your Anova is statistically significant, you want to carry out pairwise comparison. We call that a post hoc. And what I want to do, I could run a Tukey HSD if I wanted to. It's perfectly fine, but I want to show you another model or another way of comparing means pairwise that also does not inflate, let's just say it adjusts the p-value appropriately. It doesn't inflate the type 1 family-wise error rate. So what's probably equally as effective is called the pairwise t-test. And we can just go quiz over prof. Now, the first thing we have to do is we have to make sure that that R knows we're not doing a paired t-test. So we'll just do paired false. And then we need to come in and adjust. Let's see, is that right? P-adjust method. Yeah, I think this works. And I want to look at the Bonferroni approach. So what we end up getting here is we get the p-values, and I think it's interesting to compare the p-values with Tukey. When we compare A to B, the Bonferroni gets a p-value of 0.845. When A to B is compared up here, they get 0.52. You can also see that there's not as much difference between comparing C and B as there is with comparing A and B. This is where things get tricky. Both of these are acceptable ways to conduct post hoc analysis. Notice that the p-value isn't much different when we have statistical significance between A and C. So in either approach, and well, either approach, our ANOVA up here is statistically significant because of the mean difference between Professor A and Professor C. So in either one, and sometimes people get tricky here. They want to show something. They want to create they want to be able to report statistically significant difference between two of K groups, and there's all kinds of P adjustment methods that you could use. So they'll go through and try them all and find the one that gives the result closest to what they hope to find. So I think that's a little wishy-washy. I just go ahead and I typically would report Bonferroni. I think there's nothing wrong with reporting Tukey. Just be consistent with it. Guys, next we're going to get into effect size. Now, effect size is going to drive you crazy, drives us all crazy. But essentially, effect size looks at the mean difference based on controlling for the sample size. Now, if we go back over to the to this. And let's just think about it in the simplest case, okay? Let's say that we've got, looking at a sample mean difference, and we have one mean that's 32 and one mean that's 30, and we have a standard error of 2. Now remember, standard error is always a function of sample size for the t-distribution. Well, degrees of freedom, so ultimately sample size. And what we would have here is we would have a test statistic of 1, which would create a p-value greater than or equal to 0.05. We would not have statistical significance. But if we bump up the sample size where that same mean difference has a standard error of 0.25, then we have a 2 over 0.25, and we have, what is that, test statistic of 8. Guys, this would be statistically significant at the 0.001 level. So the mean difference based on the sample size could create statistical significance or not. So there's been a lot of debate on that in the statistics community over the years. So Cohen came in and created something called an effect size, which examines the mean difference. Now, at the end of the day, effect size is just something that allows you to compare your research results with other research results controlling for sample size. So that's a really good way to think about that. Now, one thing I want to point out to you in this video is if you go to your Blackboard site, you can see that I've uploaded something called effect size magnitudes. And if you click that, what it's going to do is it's going to take you to this this really cool rule of thumb on magnitudes of effect sizes, and it's you can kind of consider this to be far more than you ever cared to know about effect sizes. But you can't hardly get anything published these days without talking about effect size for the statistical technique that you are using. Now, what I want to do is I want to show you how we calculate effect size for ANOVA. And for the full ANOVA, the ones that I want to show you is one called the eta squared. And guys, this is nothing more than the square root of the multiple r squared, which we can easily get. And then the other is the omega squared. Probably, I would say for the full ANOVA, the omega squared is probably arguably the most appropriate. The omega squared looks like a W, and that is the ugliest omega in the history of omegas. But it would be the sum of squares between minus the degrees of freedom between times the mean square within, all over. Let's see, guys, I forget. Sum of squares total plus the mean square within. Yes, that's right. Okay, so I'll show you how to get. And then, well, I should say here that the square root of our omega squared is our effect size. All right. So two ways of assessing the effect size for our full ANOVA. And I'll kind of drop the ball on here in just a second. Ultimately, effect sizes for our full ANOVA are really not that interesting, and I will point out something that I think is more interesting. So guys, let's go back over to R, because that's the way we do our calculations in this class. And if I can find R, yeah. And so to find the eta squared, we need to find the multiple R squared. And that's really easy to do. Just do summary dot linear model of our model that we created from our ANOVA. And you can see right here that we get our multiple R squared, which is 0.4604. So I can find my eta squared by just taking the square root of 0.4604. Right? Yeah. Okay, it doesn't like eta squared, so sorry. Okay, so eta, well, I have no idea why I did et q squared, but it doesn't matter. So our eta squared is 0.6785. Now, the benchmarks on these eta squared are run from 0.02 to 0.13 to 0.26. So 0.02 would be a weak effect. Tried to do it again. So 0.02, as I understand it, to, well, out to 0.13. Out to a 0.30, or I think actually they double that, and we'll call it a 0.26. So, well, I wouldn't call it a strong. I would call it a large. All right, so you can see that we have a what, a 0.67. So we're putting out. We have something we could report as a large effect size. The omega squared is the. So let's calculate omega squared. And to do that, we'll need our model. So I'm going to do summary of our model. So I want my ANOVA, because this, the calculation here deals with sum of squares and so on and so forth. So, so guys, in the numerator, we need our sum of squares between. And looking up at our sum of squares between, guys, remember sum of squares between was what was in the numerator. So that's going to be our 20.13. And we need our degrees of freedom between. And we need our mean square within. Well, guys, our mean square within would be 1.967. Now, we need all of that divided by the sum of squares total. Now, your output doesn't give you the sum of squares total, but we can do some mental math here. We can add the sum of squares between and the sum of squares within. So what do we get? 2043.73 plus the mean square within, so 1.967. All right, so our omega, did I get that right? Yeah. Our omega squared is 0.354. Now, the threshold or the benchmark for omega squared, well, guys, remember, we have to take the square root of that. So our effect size is going to be the square root of omega squared. So the effect size for our total model, for our overall ANOVA, is right around about 0.6. Now the threshold on this runs from, let me just copy and paste this right here. Actually runs from, let's see if I remember this right, 0.01 was weak and 0.06 and 0.14 on omega size. And the effect size here was, you know, looking at 0.60, we have clearly a large effect size for the total ANOVA. Now, guys, again, depends on who you talk to, and I guess in this class you talk to me. I don't consider overall effect sizes for ANOVA to be that cool. It's something you would report, but I think far more interesting would be the effect sizes for, I'm trying to get all my paper here, get it straightened out. Effect sizes across group comparisons would be much, much more interesting. So that's what I want to do now. I want to investigate I promise you I can spell, I just can't see. So investigate effect sizes across group comparisons. All right. Now, to do that, we're going to have to load a package. So I'm going to install packages. And I have to install something called Compute ES. Now, I want to scroll all the way down, US, California 2, because I like these UCLA folks. Once we do that, it'll go through an annoyingly long delay. Now, next thing we need to do is access the library. Guys, remember, when you install a package, it has to be in quotations. When you access the library, it doesn't. Now, there's something called MES, and that's just, MES stands for means to effect size. And let me go back over here. And so in this compute.es package, we're going to use a command that's called MES. And again, this just says means to effect sizes. So it allows us to put in descriptive statistics and come up with the effect size given mean, standard deviation, sample sizes. So what I'll put in first is I'll put in x bar 1, x bar 2, the standard deviation for the first group, the standard deviation for the second group, and then my sample sizes for N1 and N2. So first sample information and second sample information. And what this will do, it'll give me a lot of really cool stuff. So let's get back over here and do that. So it looks like to me that the cool stuff going on here is between what did our was it A and C? Yeah, and although I would compare all pairwise or I would compute all pairwise effect sizes, I want to illustrate this by focusing on A to C. So my illustration will focus on Prof A and Prof C comparison. More specifically, we're going to get the effect size for that particular group mean difference. So what I would do, I'd need some descriptives, so I would go t-apply with quiz, cross prof, and I would look at the mean. Next thing I'd want to do is I also need the standard deviations, and the next thing I will need the sample sizes. Now, we all know the sample sizes here are 5 in each group, but you know, on your homework assignment, your research, whatever it may be, you may run into sample sizes of, you know, whatever. So that's the easy way to get sample sizes. All right, guys, what I will do now is run MES. So again, I want to compare C to A. So the mean for Professor C is 5. The standard deviation is 1.58. I'm sorry, that's not the way it goes. Mean of C is 5. What are we doing? C to A? Yeah, okay. Mean is 2.2. Standard deviation for C is 1.58. Standard deviation for A is 1.30. And sample size is 5. Now, what will happen is, you know, we get a lot of cool stuff here, and I have to tell you, some of this stuff I don't know what it is, but nevertheless, I know what the important stuff is. First thing we need to look at is this D. Now, this stands for Cohen's D, and I want to come in and get some split screen action going on here, so I can not only look at R, but I want to be able to do some stuff. All right, so what we have here is D gives us our mean difference. So it's the effect size for the mean difference, and at the end of the day, guys, D is nothing more than it takes the mean from sample 1, examines that mean difference while dividing out by the standard error within. Now, this standard error within is nothing more than just a kind of a recalculated standard deviation, kind of a combining of, well, heck, I'll just show you what it is. The standard error within is, let's see, be the square root of n1 minus 1, 2 minus 1, over n1 minus 1 plus n2 plus 1. No, minus 1, my bad. So it just sums up the in the denominator, the degrees of freedom for each. So so that's what we end up getting for the for the difference there. And in case you want to know, the variance for this is let's see, n1 plus n2 over n1 times n2 plus d squared over 2n1 plus 2n2. So this is the variance of this. Now, what happens is, kind of interestingly, this effect size D tends to overestimate the population parameter. So you got to remember, guys, that you know, we're taking this information from a sample and trying to make a general statement. The research shows that this D that we get, this 0.194, tends to overestimate the true population parameter. And what some people recommend is reporting what's called Hedges G to control for this. Now, just as with Cohen's D, this thing is scale-free. It doesn't matter whether you're looking at minutes or hours or pounds or whatever it may be. It's scale-free. Think of kind of like a z-score. And this thing depends on a factor of j, this j factor. And ultimately what we'll see is that this Hedges G is just nothing more than this factor of j times Cohen's D that we got over here at 1.94. The factor, guys, is, 1 minus 3 over 4 degrees of freedom minus 1. And guys, your degrees of freedom here is just n1 minus 1 plus n2 minus 1. Okay? So, so in our situation, our G will be whatever this J is times our D, which is 1.94. And this value will turn out to be the 1.75, which we see from the output right over here. So the effect size for the comparison of Professor A, the mean difference between Professor A and Professor C, is probably most appropriate using this Hedges G. Now let's go ahead and let's make sure that this all works out correctly. Because if we get this, we get 1 minus 3 over. The degrees of freedom would be, what do we get? So 5 minus 1 is 4, plus 4 would be 8. So 32 minus 1 is 31. So if we go over to R, we're going to get that 1 minus 3 divided by 31 is 0.903. So guys, when we take Cohen's D of 1.94 times this factor, 0.9032258, we're going to get the 1.75 that we see up here from the output. And this is just a 95% confidence interval that we get. So, guys, our, our effect size for that particular pairwise comparison turns out to be 1.75. Now, at the end of the day, that really doesn't mean much unless you know the benchmarks for the comparison. And it turns out that the benchmarks turn out to be 0.2 to 0.5 to 0.8. So we have a difference of 0.3 between the weak effect, moderate effect, and large effect. Okay, so we had what was it? 1.75. So we can talk about a large effect. Now, guys, a little bit more, just a little bit. What can we say about effect sizes? Really, effect sizes depend on having a measurement scale that is meaningful. These effect sizes are ultimately standardized scales, but we need not an artificially or like this artificially created new scale that someone comes up with. It needs to be a scale that the difference in the means is a good measure, and that the measurement scale is meaningful. Another thing, it works for ratio scale data. It doesn't work with interval or ordinal data. For example, if we had the place that you finish in a race, which would be ordinal data, effect sizes aren't appropriate. Again, they're a standardized measure. So, another way, I guess worth talking about is G can also be calculated by taking the mean difference, and if you have the mean square error, it can be calculated by taking creating the standard error by taking the square root of the mean square error term. I don't know, any other interesting facts about effect sizes? Yeah, I'll tell you what, let's talk about variation within the distribution. Let's say that we have an experiment number 1, and we see that the mean difference between the experimental group and the control group is 10. And we have another experiment, experiment 2, and we see that the difference between the experimental and control group is also 10. But we have information that says that the standard deviation of the first set of scores is greater than the standard, I should say the standard error within of the second group of scores. So this standard error, in both cases, just think about it, we've got a standard deviation for each of these groups of scores. And this is a way of combining those standard deviations. So we combine the standard deviations for both of these in experiment 1, and we combine the standard deviations for both of these in experiment 2, and we see that the standard deviation is bigger than that. Is there anything that we can conclude from that? Well, what we can conclude from that is that the effect size for experiment 1 will be less than the effect size for experiment 2. Now, the reason being is if we take, again, we're assuming that we have the same mean difference. So let's say that mean difference is the difference from here and here. And we have distribution over here that has that particular combined standard error versus this, because we're assuming that this standard error within is less, so we're assuming less variation within our distributions here. But what's going to happen is, because there's more variation in these distributions, there's going to be more overlap. So our effect size will be lower here than it would be to examine this mean difference for rather obvious reasons. Gang, I think that's about all the damage I can do to you in terms of effect sizes. I don't really know anything else. Yeah, I do. One more thing I want to throw at you, and then I'll show you how you write something like this up. What if we don't have equal variances? There's something that we can do, and it's worth, I think, taking a look at it. So we violated the homogeneity of variance assumption. What can we do? Well, there's something called a one-way test, where we can, in this case, take the quiz across our group, which is the prof. That's kind of cool because the one-way analysis of means here does not assume equal variances. But in this test, you lose power. And you can tell that when we assumed that we had equal variances, that our p-value was 0.025, I believe it was. But when we don't assume equal variances, our p-value is inflated. Well, not inflated, but it's just higher because we can't assume equal variances. So this is something that you can put in your bag of tricks if the HOV is homogeneity of variances is violated, and you kind of get evidence of that, or at least reason to believe that from Lavigne's, then you might consider conducting this test. I probably wouldn't. This is just kind of a, here you go, this is an option. I would probably just go ahead and carry out the Anova and then just report that Lavigne's test was statistically significant. All right, gang, let's see how we would write something like this up. I'll bring up a blank document and show you based on the results. So I would say that there was a significant effect of, I'll tell you what, let's do. I don't have this stuff memorized, so I need to go back up to the Anova. All right, right there's what I need. So, where did it go? All right, so I would say there was significant difference. Well, that's not the way I would say it either. So I would say there was a significant difference in mean quiz score across professor. And then I would report this. So I would report the letter of the test I used. I used the F statistic here because that's the underlying probability distribution that models the comparison. My degrees of freedom are 212. The F statistic is 5.12. And we are statistically significant at the 0.05 level. With omega, what was our omega? Does anybody remember? I don't. Okay, our omega was 0.60. So I would come up here, go to insert, go to symbol, and choose omega. I believe this is it right here. So omega equals, you guys need to get back into point 60. All right. Despite a large effect size, Bonferroni post hoc test revealed non-significant differences between non-significant differences between quiz scores for Professor. All right, guys, losing my place here. Let's get to the all right, Professor. Okay, so we non-significant differences between professor scores for Professor A and Professor B. And between Professor B and Professor C. However, a statistically significant difference was revealed between Professor A and Professor C, right? Yes. And our p-value here was less than 0.05. And our effect size was 1.75. Now, I think that's okay. The gist of it is we, first of all, talk about our overall model. Then we dive into examining the post-hoc comparison along with the effect size for each of the group comparisons. So obviously, guys, you would want to don't forget, insert descriptive stats beforehand. I'd want to talk about the entire 15 scores, and then I'd also want to look at mean standard deviations across each of the professors. So, guys, I don't know if there's any more damage I can do here. I don't know how long this thing has lasted, but it feels like it's lasted a long time. So I'm going to wrap it up. Say that's it. Take care.